So welcome back to the live broadcast of Asteroid Day. It's now time for us to have a Skype call with the United Arab Emirates. And I'd like to say good afternoon and a warm welcome to Dr. Ilias Fernini.
Good afternoon. How are you doing?
We are doing very well. And how is everything over there?
Oh, it's fine. It's very hot.
Mm-hmm. I know that the United Arab Emirates, you've been doing a lot of activities around Asteroid Day. You've had everyday shows and competitions and so forth. So enlighten us a bit. How has it been?
Yes, yeah, we are having a very special Asteroid week of activities just to celebrate the 30th of June, the Asteroid Day. So every day we have here at the Sharjah Center for Astronomy and Space Sciences, we have competitions, we have lectures. We have even a special asteroid observing night. So we're observing the asteroid Vesta since more than 2 weeks. So every night we invite the public to come and also wonder the beauty of the sky.
Yes, because I know, asteroid Vesta is the second largest object in the asteroid belt. So how have the observation been going? Has anything happened so far?
Well, as far as we know, so asteroid Vesta is the fourth in terms of size. So we have been observing it every night for a couple of hours. It does move a little bit slow. So what we're doing, we are taking pictures every 10 minutes, and then we stack all the images to see how the asteroid is moving. So it is an excellent experience for the people to see that things for sure move around.
Lovely. Well, thank you so much for participating with us, and have a continued great day. Thank you. And with that, over to Brian Cox.
Thanks, Sabinije. Now we have a panel, well, it's science time, essentially. We have a panel on the role of asteroids in shaping planets, our solar system, including the Earth, the Moon, and the origins of life. If I could start with you, Patrick. We often hear that asteroids, exploring them is part of the key to understanding the formation of the solar system. So why do we say that?
Yeah, so this is true. In fact, the solar system was formed about 4.567, this is easy to remember, billion years ago.
About.
Yeah, about, yeah, with some error bars, but anyway. No, actually, the reason why we know that is thanks to asteroids. So this is actually a piece of a meteorite. And you can see on this meteorite, so that comes from asteroids basically, you have little inclusions which are called calcium aluminium inclusions, and they date the time zero of the solar system. This is the oldest material you will ever find, because the oldest material on Earth is much younger, because the Earth was cooked, was transformed in terms of chemistry, yes, sorry. And therefore, if you want to go back earlier in time in the solar system, you need to access rocks which never experience big heating processes, etc. And asteroids are so small that they contain the original composition of the solar system. And this is a piece of meteorite where you can measure the time where these elements were formed. And I have in my hand the oldest elements. So that's why asteroids are very interesting, because they allow us to do that. And the reason is that initially the solar system was the sun surrounded by a disk of gas and dust. And these dust collided gently together and started to agglomerate to form eventually bigger bodies we call planetesimals, then embryos of planets like Mars, and then eventually some of them ended up into planets. But the rest went into Mars and Jupiter, where now we have the asteroid belt. And therefore these asteroids are the bricks of the remnants of the planet formation. So they are kind of a queen of the solar system, because they really allow us to trace back the history of the solar system. And actually, we give them the names of goddess of Greek mythology, the first one. So queen is a good analogy.
Now, Alan Fitzsimmons, welcome. We haven't met you before, the Professor of Astrophysics at Belfast. So there are different kinds of asteroids, and there are also comets. There's a population of small objects out there. So could you describe that population?
Well, it's difficult because there are so many. When we think of an asteroid in our heads, quite often we think of just a normal type of rock. But we know from our observations from telescopes of asteroids throughout the solar system that there's a huge variety of these types, of these compositions. And we go from the inner asteroid belt, where we see primarily very rocky objects, almost similar but not quite the same as the rocks we would find on the surface of the Earth, out through to the outer edge of the asteroid belt, where we see rocks that are very much more rich in elements such as carbon. They almost look like pieces of coal or soot or charcoal. And when we go even further out, we see objects that have a lot of ice within them. And these form the comets that we see. Now, when we look closer in towards the sun and we look around the Earth, we see all these various types of object there in near-Earth space. And in fact, it's been a process of discovery over the past decades that we find that in the near-Earth objects, we find all these different types of asteroid, and of course comets as well passing by. So by going and investigating near-Earth asteroids and the near-Earth comets, we get a sample of what the entire solar system effectively has been made from.
Patrick Helminger, so welcome to Asteroid Day. You're an asteroid expert, meteorite expert, and you have a couple.
I have one. I brought 2 meteorites, and I have one meteorite here that fell in Mexico in '69, and it's actually the same one as Patrick had, and it's grey, so it contains a lot of carbon. Carbon is the atom that is most important in our bodies, and it not only contains carbon, but it contains molecules, complex molecules that build up proteins, that build up even our genes. So we can suppose that if these materials are very pristine, that did not get changed, that they came and seeded the Earth at the beginning, because conditions at the beginning of the formation of Earth were very unfavorable. And so the start of molecular formation could well have been in asteroids. And here we have a piece that brings this back to us. And I brought another one. It fell in 1960 in Australia and has a beautiful name of Milby Lily. And in its mineral structure, it contains water. And this water has exactly the same signature as water on Earth. And now we know through observation, and especially since probe Dawn went to visit Vesta, the asteroid Vesta, that it's from Vesta. So we can suppose that the water that came to Earth, that formed our oceans, rivers and lakes, that at some point when the Earth cooled down sufficiently in the beginning, was brought down by asteroids from the same time probably as this same meteorite that fell only a couple of decades ago.
And I suppose it sounds surprising to many people, because of course today the solar system is pretty quiet, but the idea that they could deliver enough material sounds surprising. But Rusty, the history, the impact history of the solar system is written all over the surface of the moon, isn't it? So it didn't used to be this quiet.
No, it definitely was not this quiet, especially in the early formation of the solar system. And we have a period that all of the scientists have declared somewhere between 500,000 years after the formation of the solar system and a million years after the formation of the solar system, where the late heavy bombardment occurred, and many of the biggest craters that we see on the moon were formed. And there were similar impacts with the Earth. I mean, people look around the Earth today and they say, well, why are you worried about asteroid impacts? I don't see any holes in the ground. And there are about 200 of them. But that's totally misleading, because if you look at the moon, which is not protected by an atmosphere and is not a living body, but is sort of a static, dead body that lies unprotected, it's filled with craters. Craters on craters, you know, they're just all over the place. That's really what the Earth was affected by, but we're protected by the atmosphere. Mark will talk about that in a moment. But the fact of the matter is, Brian, that we live in a shooting gallery, really, that occurs today. Millions of these near-Earth asteroids, the ones that have an orbit that have been kicked out of the main belt and come by the Earth, and occasionally hit the Earth, but those flood by the Earth every day. But we're protected from most of them, and even the ones that hit, they get turned over by the living Earth, volcanism and other things, so that it appears as though we don't really, these aren't really a threat. But the fact of the matter is the Earth is being bombarded even more than what we see on the moon. So it's a little misleading.
It's quite surprising as well. I'm looking at that picture behind you as you speak. You
Yeah.
see that atmosphere, which doesn't look like it should be capable of protecting us very well. But it does. But then it's a complicated question, isn't it?
It is a complicated question. So one of my earliest and fondest memories is of my dad letting me look at the moon through his binoculars. And just a very cheap pair of binoculars, anybody can do this, and it's beautiful. Especially if it's less than half full, you can see these craters that Rusty talked about, and if the light is right, they're so vivid, it looks three-dimensional. It looks like you could reach up and touch it and feel it. And we've all seen the images from the Apollo missions, and these craters go all the way down to very small sizes. And those small craters are created by very small impacts. Those are the ones that do burn up in the Earth's atmosphere. And they burn up, but the energy doesn't go away. So while they don't get to the ground and make a crater, they do release their energy in the form of an explosion, like Tunguska, which is what we are celebrating. And those can be very damaging on the ground. In fact, they can be more damaging. They could be more dangerous if that energy is deposited at high altitude. The shock wave, the blast wave from that, the same blast wave that blew all those trees down at Tunguska, could do tremendous damage to a city or to people or anything else on the ground.
And Tunguska is a small impact. I mean, we see, for example, the Schumacher-Levy 9 impact on Jupiter was it punched an Earth-sized hole ultimately in the clouds, didn't it?
That's right, and it shot up a plume of debris. The plume of debris came back down, and that created the scars that we're seeing above the cloud tops of Jupiter. And those scars were bigger than our entire planet.
And this is one of the things that I think surprises many people, that the Earth is not an isolated object. As you've described it, the history of the planet is that impacts were critical in delivering the Earth that we have today, but they're also a threat. I mean, how dynamic is the solar system today?
Oh, so in fact, early it was very active in terms of dynamics, because Jupiter, the giant planets were formed very early in the solar system history, like the first million years. And then, according to some scenarios, including some developed in Nice, the giant planets started to move and come close to the sun, like we see actually these hot Jupiters around other stars, very big planets close to the star. But because there were two, there were Jupiter and Saturn, at some point they reversed the direction and went back. And this planetary dance mixed a lot of material, the material that was formed beyond what we call the snow line, which is where the ice, the water condensates, could come in the inner solar system and mixed with the material which is more refractory, formed close to the sun. And this is why in the main belt, by the way, we have this sort of a very diverse composition in the asteroids in a very narrow region. And by these planetary motions, of course, you had a lot of impacts going on. And even big planetesimals like the moon is now understood as the outcome of a big impact of a Mars-sized body with the Earth that make a debris disk, and then the moon could reaccrete. So that was called giant impact era. And then we had smaller impact, slightly declining, and we believe effectively that during this era, the material of asteroids like water and organic material could come to Earth and therefore provide all the elements that are needed for the emergence of life. And this is why we want to get samples back from asteroids now with Hayabusa 2 and OSIRIS-REx. We chose specifically these kind of bodies which we believe are rich in carbon, because we want to be able to study in the lab the structure of the organic material and check whether it is consistent with the structure of the organic material that we think can be at the origin of life.
Is this well established now? Because every time we go to a comet or an asteroid, we see, and sometimes we see the water is of a different isotopic composition, and sometimes it's the same. Are we beginning to suspect now that really it is true that much of the water on Earth and the organics, the seeds of life, came from impacts?
I think that's right, because one of the big surprises from the ESA Rosetta mission was that the composition of the water at that comet didn't match what we find on Earth today. And that forced us to look in other directions. And in particular, we've got a set of what we believe are icy asteroids out there, out in the distant asteroid belt between Mars and Jupiter. And when sometimes we see them even behaving like little comets. We call them main belt comets. And that's now our focus on the possible source of the asteroid or of the water here on Earth, because as we've heard,
I think Rusty had a comment as well.
Yeah, I think it's very interesting if you think about it, Brian, that how related asteroids are to life. I mean, we're fascinated by life. How did it start? Where did it come from? What's going to happen in the future? And this is all tied up in asteroids and a few comets too, but asteroids mainly. And it is both, as you said, the source of so much many of the components that allowed life to form on the planet. But then once life got a toehold on the planet, then large impacts become a challenge. But happily, in the interim, we've developed a brain and a bunch of machines which are going to allow us to predict if we're going to get hit and prevent that from happening. So life is just intimately tied with asteroids, and if you're interested in learning about life, you got to be interested in asteroids.
Richard Dawkins is going to be on in a couple of minutes actually talking about that. I just got a message saying time is over, and it sounded quite urgent, in fact. I want to talk about this, which is a different kind, very heavy metal one, isn't it?
Yeah,
give me the 1 second, because time is over. Yeah. This weighs a lot.
I think it's very important to know what composition of asteroids have to be, because if you want to go there and do something, this one we can knock, and this one we can't do anything, because it just flies apart. Yeah. If you put a hammer on it, it becomes dust.
So you need to know what they're made of to deflect them.
You can knock it away.
We'll pick this up afterwards, but for now, time is over. Okay. So over to John Luca.